Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour, episode 48 for Monday, May 31st, 2010. What's up with physics? This episode of Dr. Kiki's Science Hour is brought to you by Squarespace.com, the fast and easy way to publish a website or blog. For your free trial and a 10% discount, go to Squarespace.com and use the offer code Kiki. Welcome, everybody, to this episode of Dr. Kiki's Science Hour. I'm Dr. Kiki Sanford, and this is a show where we talk about science for an hour, or at least pretty close to that. And today I am joined very graciously again by Anil Ananthaswamy, the author of The Edge of Physics. We talked with him in the last show about the Large Hadron Collider, and we talked about, everything that we could possibly think of, and I'm sure there are some more issues out there. I'm sure there are more things that we could talk about related to the Hadron Collider. But we're here today to talk about physics and what's up with physics these days. Anil has been writing about physics and working in the area of physics in journalism for a while, and I know there are more chapters in his book, The Edge of Physics, than what we have discussed so far. So maybe we can start off by finding out, Anil, if you're up on any really interesting physics developments over the last couple of weeks, things that have been kind of caught your fancy.
I think we briefly touched upon it in the last show on the Large Hadron Collider, and that's the issue to do with the matter-antimatter asymmetry. This big question that is there in physics today: what happened to the antimatter in the universe when the universe began in a Big Bang? Matter and antimatter is supposed to have been created in equal amounts, and we don't see any of the antimatter. So there was a development in the last couple of weeks that was actually quite nice, coming out from Fermilab in near Chicago.
Oh, I think I read something about that. Something to do with the neutral. Oh, I can't remember the name of the particle.
It's a B meson.
B meson. There we go.
B meson, and that B meson sort of decays, and they figured out that it was decaying a little bit more into matter particles than it was decaying into antimatter particles. And essentially, one of the sort of ways in which you can answer this puzzle about what happened to the antimatter is that maybe in the early universe there was some asymmetry between matter and antimatter, and maybe a little bit more matter got created than antimatter. So what's left over now is that little bit extra matter that was created. Everything else kind of just annihilated and became energy, and we were left with that tiny excess. And at Fermilab, I think it's still early days, but they did see signs of this kind of asymmetry, where you have a little bit more matter coming out of a process than you have antimatter.
Yeah, I think that's one of the interesting things that we have to see is look for those little tiny clues of are there clues as to other particles that might be involved? Are there clues as to a certain proportion of the particles decaying a certain way or another way? And what are the clues that physicists really have to pay attention to be able to answer this question of how we ended up in a matter-filled universe?
So there's in the second chapter of my book, in which I visit an underground mine in Minnesota. The mine, the experiment that I was actually going there to see was experiment looking for dark matter. But what was actually much more fascinating about that mine was that they had actually built almost about 15 years ago an experiment that was looking for clues to these kind of theories about matter, antimatter, asymmetry. So about maybe about 2-3 decades ago, there was a lot of theoretical work that went on, which told us how this kind of asymmetry between matter and antimatter could have come about in the very early universe. So just after the Big Bang, like fractions of a second after the Big Bang, the theories were showing us maybe, sort of 1 in 10 to the 10 particles was matter as opposed to antimatter. There was an excess of 1 in 10 to the 10 particles that was in favor of matter. And one of the consequences of these theories was that the proton, which makes up which is one of the constituents of an atom, the proton should decay in something like 10 to the 32 years. So any given proton has a half-life of about 10 to the 32 years. And, you can't really, that's
a long time.
That's a long time. You can't just watch one single proton and wait for it to decay. You can't do that. But physicists figured, what if we assemble, 10 to the 34 protons? Maybe then you have a chance of observing a couple of protons decay in the lifetime of the experiment.
Right.
So and that was one of the interesting things that started happening about 10-15 years ago, where people started monitoring these huge numbers of protons. It could have been protons in a giant tank of water. Or in the case of the Sudan mine, what they were doing is they basically had iron. They had, I forget the numbers now, but it was almost 1,000 tons of iron or something like that, which was taken deep into the mine to the very bottommost level of the mine. And essentially they had instrumented this whole thing to be able to watch all these protons in that mass of metal to see if anything decayed. Of course, they didn't see anything like that. But there was a lovely story to do with when they were bringing down these modules of iron down the mine shaft. The technician who was explaining all this to me, he's been around with the physicists for a long time, and he's like he calls himself the child minder for all these physicists, because
the child minder.
pretty much because the physicists are always asking him, how do we do this little bit, and how do we fix this problem, and they're half a mile underground in a mine, very far away from any hardware store, and he has to always keep coming up with these, wonderful little sort of tweaks and stuff that he makes up on the fly to help them with their experiment. And he was talking about how when in the early days of this mine, they had to bring down these really heavy pieces of the experiment. It was called the proton decay experiment. And it came down in sort of modules of I think there were some 256 modules that had to be brought down the mine shaft, and they didn't have enough money to sort of set up floodlights where they were working at the head frame of the mine. There were two things that were happening. One, they had to work at night because during the daytime, the mine was being used by the Minnesota Department of Natural Resources that was conducting tours for tourists. So the mine was off limits for the scientists. So they had to work at night, and they didn't have enough money to sort of set up a huge number of lights. So they had these tiny little flashlights on their I think truck or something, on the crane. And unfortunately, there were some stickers on these modules that were coming in, which had stickers saying that this whole cargo was radioactive, and these were just basically some tiny radioactive things that were needed for calibration. But according to nuclear safety laws, they had to the trucks had to carry the stickers saying this cargo was radioactive.
Yeah.
So. And Jim, this technician, was telling us how they would be working at night with these two tiny headlights, and he would see sort of camera flashes out in the forest. People were taking pictures thinking that the government was dumping nuclear waste into this mine, which of course it wasn't. But,
and they're not telling anybody about it, but there's nuclear waste going in here.
And they were doing it at night. And it was you can go down into the mine and see the remnants of these sort of Sudan, the proton decay experiment that they carried out in that mine. the upshot of all these experiments was that they didn't see anything. There were a couple of experiments in, oh, there you have it on your screen. That's the view as soon as you enter the Sudan mine. That particular experiment is a new one that you're looking at. I think it's the Minos experiment.
Yeah, from Minos.
Neutrino, yeah. That's relatively new. So the proton decay experiment now is dismantled. You can't see it anymore. You just see pieces of it lying around. And that predates the one that you're looking at on the screen. There was another interesting fallout of, so it was not just in this mine, but there were a couple of mines in Japan, for instance. There was a experiment called the Kamiokande detector, which is also looking for proton decay, but in a large tank of water. It was essentially monitoring a huge tank of water. And the idea is if when a proton decays, there will be a flash of light, and they had all these photomultiplier tubes that were lining the tank looking for this flash of light.
I found an image from the, I believe, the proton decay experiment. Kind of hard to see in this. There we go.
Oh, there you, yeah. I think that might be it. I can't.
But what you see are the these little detectors along the side of the tunnel that are basically all these little what you're talking about with the Kamiokande detector, which are the photomultipliers, right? Where they
photomultiplier tubes. Yeah. I think the Sudan mine didn't have the Sudan's proton decay experiment was not a photomultiplier tube. They had some sort of it was a different kind of technique they were using to detect the proton decay, more to do with ionization currents inside the detector. But the very interesting that happened in the Japanese mine was that the tank of water that was essentially being monitored to look for proton decay, suddenly in 1987, there was a supernova that went off in the Large Magellanic Cloud, and the supernova spewed out neutrinos. And these particular tanks, there were not just one, but three different ones looking for proton decay in three different mines around the world. All of them lit up because neutrinos, when they come and hit a molecule of water in the tank, they also create a flash of light. And these experiments, which are looking for something completely different, ended up seeing neutrinos from deep space for the first time. And in fact, we've never, ever seen a neutrino come from outer space apart from that one incident in 1987 from the supernova.
That's the only time. So,
that's the only time, and that was an accident almost. We were not even looking for it.
But now we have detectors all over the place.
Yes.
Neutrino detectors that we're putting all over the place, trying to detect them on purpose, and we still haven't.
Yeah, essentially, we're looking for neutrinos from deep space, and the only ones that we have seen, apart from that one supernova, are neutrinos from the sun, which we know and love, and we've learned a lot about neutrinos from the sun. And the other neutrinos are the ones that come from the atmosphere. When cosmic rays come and hit the Earth's atmosphere, they generate neutrinos. And so all these experiments that are actually looking for neutrinos from, from really deep space are at this point they've only seen neutrinos either from the atmosphere or from the sun. And the only things that have come from further away from the sun is this one incident in 1987. And that, of course, again, they were detected by detectors that were not actually built to look for neutrinos. They just happened to have the same technology, and they ended up seeing neutrinos. The picture that you just showed, that's the Super Kamiokande, I think. That's I've been inside that detector. It's you can see someone in a boat, right?
They're individuals on what looks to be a water surface in a little inflatable boat.
Yeah, it's a huge tank. I forget the total volume, but it's tens of thousands of gallons of water that's being monitored by these 11,000 photomultiplier tubes. And as they're filling it up, these people are actually in the boat. And when I went there, so what had happened was that this particular experiment had been running for a while, and maybe in the early 2000s, there was one of the photomultiplier tubes cracked, and these are vacuum tubes, and the crack just caused the vacuum tube to implode, and that set off a shock wave, and the shock wave then ended up sort of destroying about 2/3 of the 11,000 photomultiplier tubes. It was a huge explosion in the tank.
I think I
And there was
remember
one-
hearing about that. Yeah. That's, I mean, it's,
yeah, no,
it's,
it was quite a big event at that time.
yeah.
And so when I went in 2006, and they had just finished repairing the whole thing, and they were about to fill it up with water. So when I called them up and said, I'm writing this book, can I come and visit your neutrino detector? They said, yes, you have to, but you have to come before April 15th, because once it's filled up with water and it starts working, no one's going to be let inside. So I went there just before they started filling it up with water. And it's an incredible feeling to stand inside this gigantic tank that's lined with these shiny photomultiplier tubes, and everything is reflecting off everything. So you're under it feels like some sort of scientific cathedral. And I mean, that's the one place where I've stood inside and felt like overwhelmed by the technology. It's just astounding. It's beautiful and
Yeah.
also very scientific, and quite a lovely experience.
I just wonder about the logic of putting such a sensitive detector someplace that's so geologically active. In Japan, there's all sorts of
Earthquakes.
tectonic activity, hydrologic activity. I mean, there's all sorts of stuff going on in Japan, and to have something where the detectors are so sensitive in terms of if one of them breaks, it can send off just the ripple effect that can break almost the entire detector, and then they have to drain all the water from the tank to be able to replace it, fix everything individual detector by individual detector, and then fill it all the way back up with water again.
Well, they had to change every photomultiplier tube. So essentially, they figured that these photomultiplier tubes are like television tubes. They just have a glass surface, and now what they have done is they have put sort of a plexiglass covering on top of each one of them, so that even if the vacuum tube were to break, the outer covering doesn't. And so, you can restrict the damage to one single vacuum tube, and you won't destroy everything else. But what that meant is that they had to re-engineer every one of those 11,000 tubes. And it took them, I think, about 3, 4, or maybe even 5 years to finish that re-engineering effort.
Yeah,
It was amazing.
Yeah, I've only ever seen images of it, so just pictures online, and like the ones I was just bringing up, and it just seems Kamiokande looks just like one of the most astoundingly beautiful scientific locations.
It is a very beautiful. It's in the Japanese Alps, and so even though it's a mine, you don't go deep into the mine. The mine is actually the mine shaft is literally a tunnel that's cut horizontally into the tunnel, so into the mountain. So you drive up to the mountain entrance, and then literally it's a long, I think 4-kilometer long tunnel that you drive into the heart of the mountain, and the mountain is above you, and you just enter essentially the middle of the mountain, and it's an active mine. I think they're still mining zinc out there, but there's also all these other tunnels that have been given up for physics. So it's not just the Super Kamiokande. There are other detectors. There's one called the Kamiokande, which is the earlier version of the Super Kamiokande. And then there are also dark matter detectors and all sorts of things inside these mines. And I think maybe it's worth mentioning why they have to go inside these mines in the first place. It's basically to avoid signals that are created by cosmic rays. So if you're on the surface of the Earth with no protection above, then cosmic rays can generate the same kind of signals in the water. So you have cosmic rays hitting the Earth's atmosphere, and that generates a particle called a muon. And when the muon streaks through the water, it creates that kind of flash of light that is exactly what a neutrino would create.
That everybody gets excited about it, and then they have to figure out that that's not what it came from.
Yeah, and these muons will outnumber signals from a neutrino almost 1 billion to 1. So there's no way of monitoring a neutrino if you're inundated by cosmic ray muons. So you go inside a mountain or deep inside a mine, and then the Earth above protects you from the cosmic rays.
Yeah, with the neutrinos, the one detection that was an accident, in the 80s. Now, is it that the supernova or the cosmic event that creates the high energy neutrino, is it that it has to be directed directly at the Earth for it, for us to be able to catch it? Is that the reason that one particular event was captured?
Well, that's been the only supernova that has gone off near us in recent memory, or since we've had detectors. In some sense, that kind of event has to be close enough for us to catch a decent number of them. And even though the supernova was so close by, I think the total number of neutrinos we saw were about 16 or 17, just a handful. Neutrinos, even though they might come at us in the trillions, they just don't interact. And, of all the neutrinos that must have passed through the detectors, only about 16 interacted, and that's all we saw. So part of it is, yes, I think directionality is important, but also the fact that there has been no other event close by apart from the sun spewing out neutrinos at us. The higher the energy of these neutrinos, the lower the numbers. So you have sort of diminishing returns as you start looking for neutrinos of higher and higher energies. You're actually there's far less coming at us, and you need large volumes of water that you have to monitor, and the chances of seeing one just dramatically fall.
So we're basically playing a probability game here with these detectors. We're trying to just increase the probability of capturing these really rare particles that come shooting from places other than our sun. We're finding them from, like you said, we're finding them from our sun all the time.
The solar neutrinos are now commonplace. In fact, there was a big mystery that appeared when the first solar neutrinos were detected, and that was that they were seeing a deficit in the number of neutrinos. So our theories of how many neutrinos should be produced by the sun were telling us that we should be seeing a certain number of neutrinos, and we were seeing far less than that. And it came to be called the mystery of the missing solar neutrinos. Sounds like some Hardy Boys mystery or something.
It does.
And it was a real mystery for a while, because physicists were beginning to question whether they understood the sun at all, because essentially these neutrinos are coming out from the nuclear processes that are happening inside the sun, and we were beginning to doubt our understanding of these nuclear processes because we were just not seeing enough neutrinos. But in the end, it turned out that people realized that they actually knew their nuclear physics really well. So there was very little doubt about the nuclear physics. So the mystery remained, and until eventually they figured out that what was happening was these detectors were sensitive to one kind of neutrino, and there are three kinds of neutrinos in the standard model of particle physics, and they were looking for one kind. And it turned out that even though the sun was spewing out a certain number, by the time the neutrino had traveled all the way to Earth, it had actually changed from one type to another. And because it had changed from one type to the other, the detector, which was sensitive to just one type, was not catching all of it. It was just catching the ones that had not changed. And and that was a huge discovery, because that led us to this idea of neutrino oscillations, that neutrinos, as they travel through space, oscillate between one type and another. They keep switching back and forth. And this was the beginning of the sort of crack in the standard model of particle physics. So neutrinos can oscillate only if they have some mass. And if they don't have mass, they will not oscillate. So it turns out that because they oscillate, we know that they have at least some mass. And the standard model of particle physics, as it stands, does not allow the neutrino to have any mass.
Oops.
So it's very, very clear that, exactly. So it's very clear that there is something that we need to know beyond the standard model of particle physics. So the neutrino oscillations were one of the first things that led to people realizing that the standard model was not complete.
Right, and now additionally with this potential discovery at the Fermi Lab, going back to the Tevatron that we started talking about at the beginning of the show, with the beta mesons, B mesons or beta mesons? Beta mesons.
B mesons.
B mesons.
B mesons.
That they have a certain amount of oscillation as well, and that they actually whether or not there's a particle involved in their decision to become one kind of B meson or another, one charge or another, that could actually have an additional impact on this crack
the standard
in the standard model.
Yeah. So there are a large number of sort of cracks that are developing, and most physicists would agree that the standard model is obviously it's been really well proven in experiments, but it is an incomplete description of reality. For instance, we've talked about dark matter. This matter that's we think is out there in the universe. We can only detect its gravitational influence on stars and galaxies, and we have theories about what this dark matter might be. But the standard model of particle physics does not predict any candidate particle for dark matter. So we know that if dark matter exists and if there are particles that make up dark matter, then it has to be explained by physics that goes beyond the standard model. So that's one big chunk of a whole number of cracks sitting there waiting to be explored. So neutrino oscillations and matter-antimatter asymmetry, all these things are telling us that the standard model of particle physics is not complete. We need some. And in our last show, last week, when we were talking about the Large Hadron Collider, we talked about supersymmetry. This idea that for every particle in the standard model, there is another particle called the superpartner. So the electron has a superpartner called the s electron or selectron. The photon has something called the photino, things like that. So every particle that we know of has a superpartner. And that is the most favored sort of extension to the standard model. So when people talk of physics beyond the standard model, supersymmetry would be the first big candidate theory. That's they're waiting for some evidence of that from the LHC.
Yeah, and that's they're just hoping that with the higher energies that the likelihood of catching more of those particles is once again increased. It seems like that's the game in physics. You get a bigger detector, bigger collider, more energy, higher probability of seeing these very rare instances.
Yeah, and in a sense, the experiments that have already been done, say at the Fermi Lab and other colliders that have come before the LHC, the idea is that if the universe is supersymmetric and if these superpartner particles exist, now we don't know their mass. We just, we have various models where you can have different masses for these particles. But if they exist, then they obviously are more massive than what we've been able to create so far. So we haven't created supersymmetric particles at the Tevatron at Fermi Lab or any of the colliders that came before. And they all had certain energies, and hence they were capable of creating particles of a certain mass, and we've not seen any. So we know that these supersymmetric particles at least must be more massive than what has been possible to create so far. Now, whether they are, whether the LHC energies will be enough to create these particles, or whether these particles are even more massive than what the LHC can create, that remains to be seen. We don't know yet. Yeah.
Now, I know you visited a bunch of earthbound detectors, but it seems, wouldn't it be an interesting idea to put detectors in space off of our planet to get away from a lot of the stuff that happens here on our planet, or even get out closer to astronomical events that could potentially lead us to greater understanding of these particles, that give us the chance of using a star or a supernova or something much bigger than what we have. I mean, it would take hundreds of years to get there, but thousands. We need much greater technology to actually do it. But it seems like that would be an interesting idea.
Well, space is definitely a favored location. The getting to the astronomical objects like a star or a supernova is definitely not within the realm of possibility right now, because it just it takes too much energy and time to get these things anywhere close. I mean, the farthest any probe that we've sent out into space has gone is to the edge of the solar system. It hasn't even yet left the solar system, so to say. So there's no way we are going to get to a star. The nearest star is some 4.3 light years away, and so there's no way we're going to do that in any time soon. And in terms of supernova, you really don't know when the next star is going to blow up. So there's no way to actually plan on going to a supernova. So that's not going to work either. But what they've done is essentially they've done sort of what you're saying without actually going all the way to the astronomical objects. They've got space observatories that are either in orbit around the Earth. So telescopes like the Hubble Space Telescope. The Hubble Space Telescope is, the kind of, it's not an earthbound telescope. It's up there in space, and in that sense, it avoids all the problems that come with having an optical telescope on the ground, which is basically you have to see any light that's coming from distant objects through the filter of Earth's atmosphere, and Earth's atmosphere can really mess up all that light. So what the Hubble does is just gets above the Earth's atmosphere completely and watches everything from space. But the Earth's atmosphere, the Earth itself has become quite a source of noise. So if you have a telescope that's orbiting Earth, then it's subject to sort of these kind of thermal variations that just come from going around Earth, because Earth and its interaction with the sun, going in and out of Earth's shadow, all these things can affect a very sensitive instrument. So the next best place we have now, and where there are a few telescopes already, is a place called Lagrangian Point 2. That's about, I think, 1 million miles from Earth, about 4 times the distance as the moon is from the Earth. And a few telescopes have managed to reach that point. And it's an interesting point in space where the gravitational influence of the sun and the Earth interact in a way where if you get to this point called L2, the spacecraft doesn't have to spend too much energy staying in orbit around L2. It essentially uses the fact that the gravitational influence of the Earth and the sun sort of cancel each other out. And so it's essentially a silent place, gravitationally speaking. And it's also shielded. So if the spacecraft is at L2, then if you're looking at the sun, the Earth comes in between. So you can actually prevent the sun's heat from affecting the spacecraft. And so you have all these telescopes now. In fact, the successor to the Hubble is not going to be around Earth orbit. It's actually going to go to L2. And there are 2 very important telescopes now. One is called WMAP, which is looking at the cosmic microwave background, which has been there for years now. That was launched by NASA. And so the cosmic microwave background is the radiation that's left over from the Big Bang. And recently, last year, the European Space Agency launched another mission called Planck, and Planck's also gone to L2. And they're basically monitoring the cosmic microwave background, which is essentially the temperature of deep space. It's looking at radiation that's at 2.75 Kelvin. And so the entire background radiation in space has that temperature. But it's not enough anymore to measure this radiation. We've measured the fact that the radiation is at 2.75. Now we're looking for variations in the temperature of deep space from point to point, and that variation is something like 30 parts to a million. So you're taking 2 points in space, and one might, both points are on average 2.75 Kelvin, but one point might be 30 parts to a million less or more than the other one. So you're looking for such tiny variations that doing it anywhere from near Earth is not okay anymore. So you have to get away, and so your point exactly, that they are using space as a vantage point to study the universe, but it's very expensive. It's a mission like the Hubble will cost you billions, and the same amount of money can be put. So the Hubble is a 2.5 meter class telescope, and it has cost us billions, but it has given us tremendous pictures. But for the same amount of money, you can build 30, 40 meter class. I mean, that's what they're building now, 10 meter, 20, 30 meter class telescopes, which then can be, once it's on the ground, you can do repairs, you can upgrade all these things that, unfortunately, with the successor to the Hubble, upgrades are not going to be possible. With the Hubble, at least we had the space shuttle. It could go up and it could fix it. The first time they sent up the Hubble, they had the optics slightly wrong, which was a big shock. they had ground the mirror to a slightly different focus than they should have, and it wasn't tested on the ground before they sent it up. They're not making the same mistake again with the successor, which is called the James Webb. But partly, they're also trying to be very good about the testing. It's because now it's going 1 million miles away from Earth, and there's no way we're going to be able to repair anything if it goes wrong.
No, it has to go out. It has to go out right the first time.
Absolutely.
It has to be perfect the first time. I'm going to take this moment to give a word for my sponsor. So if you'll hang on for just a second, Anil, will be just one moment.
Sure.
I'd like to thank our sponsor for this episode of Dr. Kiki's Science Hour. Squarespace.com has sponsored us. Squarespace is the fast and easy way to publish a high-quality website or blog. Squarespace has an easy-to-use user interface. It's pretty much drag and drop and move things around really easily. You don't have to know a lot about CSS to actually create an amazing website. However, if you do know CSS, you can customize it to your heart's content and make yourself an amazing website. They also have blog importing techniques. So you can, if you have a blog through WordPress or Blogger or Movable Type, you can actually import that into your Squarespace website. There are all sorts of templates for designs, so you don't have to be a design whiz to have something that looks pretty, because they've already done it for you. Additionally, they have website tracking, built-in search engine optimizer to help you rank in those search engines, which we all know is very important these days. Permission access handling, so you control who gets to have access to your website and to put things in it or on it. Additionally, they have a drag and drop Ajax interface and cloud architecture. We like cloud for speed and site sustainability and stability. We like clouds for that kind of stuff. Squarespace really is an all-in-one shop for all your website needs. They'll host it, you build it, and then you have an amazing website that people will find. And now Squarespace, our sponsor, is offering you a 10% discount if you use the promo code Kiki when you sign up for an account. So if you're going to make a blog, you can get a pretty good deal, 10% off of your website with squarespace.com if you use the promo code Kiki. So you can go there, squarespace.com. Just remember, Kiki makes it easy. And so does Squarespace. They make it easy for you to create something great. And that's our sponsor. Thank you very much, Squarespace. And now back to the science-y conversation as I move the binder over here. So we were talking just about having telescopes and detectors in outer space. I was looking at your blog, something we mentioned earlier in the first half hour, moving from matter and antimatter to neutrinos. We also touched on the topic of dark matter, and there are actually some, the Pamela satellite experiment is actually, it's detected possible signals of dark matter.
Yeah, so you were asking about what was exciting in the last couple of weeks. There was a finding which actually had nothing to do with Pamela directly. This was astrophysicists who have discovered a new type of supernova. And it turns out that it has implications for the search for dark matter. So Pamela is a Italian satellite that has been looking for indirect evidence for dark matter. The idea is that if dark matter exists, then in regions like the center of the Milky Way, the dark matter would accumulate in really sort of big numbers, because the gravity of the supermassive black hole there would suck in all the dark matter particles. Mm-hmm. And whenever there's a very high density of dark matter particles, they will smash against each other and produce a lot of secondary particles, and those are the particles that we can detect. And one of the expected signals is positrons or anti-electrons. So what Pamela saw was this slight excess of positrons coming from deep space, above and over and above what's expected just from normal processes that we know of.
Right.
They were finding a certain excess, and everyone got really excited because this is one of the expected signals from dark matter annihilation in space. And it was not just Pamela. There was another balloon experiment called Attic. And in fact, this particular balloon experiment was launched the very year that I was in Antarctica witnessing these balloon launches. So it was one of the 3 balloons that I got to see. And these gigantic balloons are launched from the Ross Ice Shelf, and they go up to the edge of the Earth's atmosphere. And there's essentially telescopes that are again trying to get above the nasty bits of the Earth's atmosphere to do their work. And Attic also saw this kind of excess of positrons. And so combined, the 2 experiments combined, there was quite a bit of fuss over the last couple of years that we might have seen indirect evidence for dark matter. Now, it turns out that this supernova, this new type of supernova, might be actually quite common, especially in the center of the Milky Way. And one of the things it produces is positrons. Well, it produces positrons by an interesting mechanism. This supernova, when the star explodes, it spews out calcium and radioactive titanium.
And that's just basically because of the pressures that are involved in the explosion. They're just slamming atoms together and creating new heavier elements. The star that explodes in this particular case is a star that has been been using helium as fuel instead of hydrogen, and consequently it produces elements like calcium and titanium. And the news reports that came out at that time, they all focused on the calcium because they were saying, that's where the calcium in our bones comes from, which is very true. Yep.
And I was thinking, these days we have titanium prosthesis, and so even the titanium prosthesis in our bones comes from these supernova. But
I love it. We're made of exploding stars.
Yes, we are all made of star stuff. It's absolutely true. But what was interesting was a little line that caught my eye at the end of the press release from these physicists, which was that the titanium is radioactive and it decays, and some of the decay products are positrons. And if their theory is right, if this new type of supernova is actually quite common, then it's possibly spewing out all these positrons that Pamela has been seeing, which basically negates all the fuss about dark matter. And so it's back to the drawing board. But again, nothing is certain yet.
Right.
We don't really know. We don't really know how many of this new type of supernova are actually there, and so
which is a crucial point.
Yeah, and there's also the possibility that a lot of these positrons are coming from pulsars, and it's the same problem. We really don't know. We don't have a estimate of the number count of pulsars, and so we'll need to do large scale pulsar surveys to know how many there are nearby and how much they contribute to the positron background and things like that. But what I find very interesting is that on one hand you have things like dark matter, which was discovered by astronomers, and it has become a big part of cosmology. We need dark matter in the universe in order to explain the structure we see out there. So it's very much a part of cosmology. And then you have things like supernovae, which is astrophysics, and then you have particle physics. All of these things are converging. They're pretty much, it's like this giant big elephant that everyone is sort of figuring bits and pieces of it from different sides, and they're all part of the same problem.
Yeah, and there's so much. I mean, even finding that there's a new kind of supernova. I mean, this is there are supernovas that we are using to determine the size of the universe, how far away and they call us the type 1a supernova our standard candle, and they're actually discovering that they might actually not all explode the same way, so our standard candle might not be as standard as we thought it was. So this feeling the elephant from all different sides, and deciding that we're going to use this particular information to make assumptions to base our next step in science on. There's a lot of going forward and then moving backwards and reassessing and moving forwards and then reassessing again.
Completely. And it's especially true of astronomy and cosmology, which for a long time, it's only in the recent past, in the last maybe decade or so, that cosmology has become more like a precision science. It used to be quite flaky at one point, where you could have error bars of 20% and it was considered okay, and that was the state of affairs. You couldn't do any better than that. It's even with data like that. When you go back to the 1920s, when Hubble discovered the expansion of the universe, and you look at the data that he collected and the plot that he drew from these data points, and you give that to a graduate student today and they'll laugh in your face, basically, because it's got all these data points and he's fitted a straight line curve through that data point, and only about 6 of them fit on the straight line. The rest of them are all over the place. So how did you fit a straight line through a completely disparate set of data points? But saying that, that was a very, very important discovery, and in a sense exactly what you said has happened, where he was using a certain type of standard candle to figure out how far these galaxies were that he was looking at. And, given the precision of the instruments of his time, he did amazing work. And it actually speaks to his sort of intuitive powers that he figured out that, no, this must be a straight line. Even though all my data points don't sort of sit on that straight line, I think the relationship is accurate. And it turns out that he was right. And as we've gone back and reassessed those standard candles, we've come up with new standard candles to figure out distances. We're essentially refining what Hubble did 100 years ago, and we still, in his equations there is this constant called the Hubble's constant, and even to this day we continue to refine the value of the Hubble's constant because it's central to any calculation we might do about the expansion of the universe, the size of the universe, and things like that.
We're refining it, but it's still lasted. It's becoming more and more exact, but he pretty much got it.
He got it. Yeah. But it's worth looking at that chart sometime just to see how amazingly far off that thing looks now when you look at it.
Yeah, there's a certain amount of I guess.
Good spot.
Yes.
On his part.
Yes. Yeah. In terms of the scope of the amount of time that things take. I mean, you've been to these big experiments that take, like you said, there's no hardware store near the Sudan mine if you're down a half a mile underground, or the LHC. It takes months or a little over a month to cool it down,
just
or
to warm
heat,
it, or to warm it up.
Just the scope of the length of the time of these things, and then we're putting telescopes in space that takes time to get them out there and to actually get data back from them once they start working. The dark matter question. I mean, stuff keeps coming in, and then the matter question. Data keeps coming in little by little. I mean, do you have any sense of timing from everything that you've been seeing and reading and I mean, or physicists that you've been talking to? Did people expect to find things within their lifetimes?
Lifetimes. Well, in the Sudan mine, for instance, in that chapter on the Sudan mine, I quote one physicist called he's on the East Coast, a guy called Richard Gateskill, and he said that this whole dark matter search. So the physicists right now are looking for a particle that they call a WIMP, which is a weakly interacting massive particle. That's the acronym for the dark matter that they're looking for. Which is also funny when you think of the other candidate they had before WIMPs, and those were called machos. Massive compact halo objects or something like that. And that has been ruled out. So WIMPs are currently the favorites. And he said that, look, in about 30 years, this entire search for WIMPs, if you were to pick up a book on cosmology, the WIMP search could be a footnote, that we might be completely wrong. Huh. But they feel compelled to experiment. And I think that's what I admire about these experimental physicists, that, they do spend an entire career. It can take something like 15 to 20 years to actually do one of these experiments properly these days. And that means, that's pretty much the peak of your scientific career. And you've devoted it to something that might not even exist, looking for something that's may not be there. And so to try and understand what drives experimentalists was fascinating. And I think it's just a different mindset. They're just driven to understand, to build instruments in ways that most people will never, come to grips with.
Yeah, which makes me wonder how best to communicate the discoveries that are being made in this science and that search. Because if you try and understand the mind of the experimentalist who is, like you said, doing something that might never amount to anything through their lifetime, or be a wrong direction. And people, the 24-hour news cycle, got to have something now.
Yeah. Unfortunately,
there are these two completely, 180 degrees from each other perspectives on the world, right?
Yeah, completely. I mean, there are people who are spending, like, if you look at the Large Hadron Collider and say the Atlas experiment, this was started in the 1990s. The design for it was started in the early 1990s. It's taken 15 years to build something, and the physicists who are at the top of their game right now have been working on it since they were graduate students.
Right.
And they will end their careers with just one experiment. And it may not find anything. Or it may. They might get the Nobel Prize. So it's that, but you can't do it because of those reasons. You have to do it because you enjoy building the experiment. You enjoy just thinking about how you're going to detect something. It's literally, the joy for them is in the process, and it's a very Zen thing as far as I'm concerned, what these people are doing, because at the end of it there might be nothing in it for them besides the fact that they spend a lifetime building an experiment.
Right. And now we have a number of experiments that are getting going. The Japanese are sending an atmospheric satellite to Venus. We've got one of the first solar sails up now, heading out around the sun. We've got the James Webb Telescope that's out. It's going to be out there.
Coming up.
Yeah, coming up. And the LHC is slowly building up its power. There was big news for the LHC this week, right? Are they? They had more intensity in their beams. So when the LHC was restarted, it had one bunch of protons going around in each beam. So there are these two beams, one going clockwise and one going counterclockwise. And all they had managed, they started the experiment with just one bunch of protons. And last week they managed to have 13 in each beam. So essentially there are more and more protons being squished into the beam now, so that the collisions will have, there will be more data coming out when the collisions happen. They're still a long way off though. Each beam will need about 2,800 bunches of these protons. And so 13 is a long way off from 2,800. But it's more than one, so...
But it's more than one. And that's a very important point, because the kind of technological challenges that one bunch presents is very different from what the challenges are for even 13. And so they've come a long way even in the few weeks that they've been running.
I'm so excited to see what comes out. I'm so excited. Thank you so much for joining me today, Anil. I know it was short notice, and you stepped up to the plate, and you've been a wonderful, wonderful guest today. So thank you so much. I really do appreciate it.
You're welcome, Kiki. Thank you.
And now I will let you sleep.
Thank you very much.
Thank you, everybody, for joining us today for Dr. Kiki's Science Hour. I'm Dr. Kiki. If you're interested in anything else from Anil Ananthaswamy, our guest today, his website is edgeofphysics.com, and his book is The Edge of Physics, which is available now if you are interested in reading about all of the amazing physics experiments that he's visited around the world over the last 10 years or so. There are the chapters in the book are fantastic. So edgeofphysics.com. The book is The Edge of Physics. His name is Anil Ananthaswamy, and he stepped up to the plate. So give him a cheer.
Thank you.
Yeah, you're welcome. And in the meantime, next week, hopefully, we will be talking about bacteria. And in the meantime, you can catch me online if you Google Dr. Kiki. I'm around and about the interwebs, at Dr. Kiki on Twitter, and I have a fan page somewhere on Facebook if you look for it. My website is drkiki.tv, but sometimes the redirect doesn't work. I gotta work on that somehow. Next week, we're changing times. 1:30 p.m. in the afternoon. So set your calendars, set your clocks for 1:30 p.m. Thursday afternoons for the Science Hour from here on out. We're switching it up because there's some changes going on around here at the Twit Network, in case you hadn't noticed. So I hope to see you then. And you can catch old episodes of the Science Hour at twit.tv/Kiki. And I guess that's about it for me. Thanks for joining me. Really do appreciate it. And if nothing else, we hope we made your world a whole lot more interesting.